When two Lewis structures are equally plausible in terms of both bonding and formal charge, how do we decide which one to accept? The answer is neither. And it's also both. In fact, it's a bit of a trick question. Before delving into the details, let's look at an example. Sodium nitrite, NaNO2, is a medical countermeasure given as the first step in treatment for cyanide poisoning. The salt dissolves into the sodium cation and the nitrite anion, NO2-. Working through the steps to generate our nitrite Lewis structure is the same as the steps that we've taken before. First, we determine the total number of valence electrons available to us as a working budget. So that's 5 electrons from nitrogen, 12 electrons from the 2 oxygens, and the negative sign tells us that it's an anion and that we have 1 extra electron, or 18 in total. Next, we identify our central atom, or atoms, and the terminal atoms. In this case, we don't have carbon, but nitrogen has a lower electronegativity than oxygen, so it's our central atom. The oxygens we'll put on either side to maintain symmetry, and we'll connect all 3 with single bonds. Each single bond subtracts 2 electrons from our overall budget, and we're down to 14 electrons in total. Those we're going to distribute around the terminal atoms first. So that's 6 on each of the oxygens, and we're left with 2 more, which will go on the central atom nitrogen. And we can subtract those 14 electrons from the remaining budget, and that's it. We're done with electrons. These are all the ones we have to play with. So now quickly checking through the octet rule and how it's applied to these atoms, we can see that the oxygens are going to have their 8. So that's 6 from the lone pairs, plus the 2 from the single bond. The nitrogen, however, only has 2 from the lone pairs and 2 from each of the bonds, so 6 in total. So it's shy from its octet rule. We know how to handle that. Now we can take some of the lone pairs from the terminal atoms and move them into a bond with the nitrogen. But here we have a different problem than we did with the cyanogen chloride. We only need 1 more bond to satisfy the octet rule for nitrogen, but we have 2 oxygen atoms to choose from. Let's write out both options and find the formal charges. So we can see that both options are equivalent. Both structures are equally likely. Following the cyanogen chloride example, we said that even unfavorable structures could contribute to the real molecular structure. If you think that this means that 2 equally favorable structures should contribute equally to the real structure, then you'd be right. The true structure is a combination of the 2 shown here. Electrons in a molecule aren't necessarily localized to 1 or 2 atoms like we see in Lewis dot diagrams. It's a limitation of the dot diagrams, and frankly of the thinking that goes into them, that this can't easily be shown. Resonance structures are what we use to overcome this limitation. To show resonance in a molecule, draw all of the equally plausible structures and draw 2-sided arrows to connect them. It's critical to remember that these arrows do not indicate that the molecule is switching between these 2 structures. Instead, you need to imagine the structure as a combination of both. You'll sometimes see these drawn using dashed bonds, like 2 half bonds. But please, for this class, draw out the full resonance structure for us on your assignments. Okay, so is that it for Lewis structures? Let's see, we've covered bonds, multiple bonds, lone pairs, formal charge, and resonance structures. So that has to be it, right?
Okay, my bad.